Hello everyone. I'm sure most of you here know how a day works. For example, if you're on the 16th of January 2038, you might expect the next day to be the 17th of January, and indeed you're correct. After that it should be the 18th, 19th, and so on. But what you might not expect is, to some computers, the next day is actually the 13th of December 1901. Why did this happen? Well, that's what we're here to talk about. It's called the 2038 problem, and if a computer doesn't deal with it correctly, we might run into a lot of problems. Why did this happen? Well, this is because a lot of computers store data in a format called the Unix Time. It's basically counting the seconds since the 1st of January 1970, and most computers store it as a signed 32-bit integer. This means that when it reaches a certain amount, it will overflow, and the first bit of that binary string is used as a sign bit, so it becomes 1, the whole thing becomes negative, it becomes 1901. There's another less well-known 2038 problem that happens in 2036 actually. It happens with something called the network time protocol, which is used by servers to store time. It again uses 32-bit for seconds, but it uses another 32-bit for fractional seconds. So this one starts at 1900, the 1st of January. So when it overflows on 2036, it will only overflow into the fractional bit, so there will be a very small error. And because this is a continuously updated protocol, the latest version, NTPv4, changed it to a 128-bit problem. Therefore, it's considered solved. What we need to worry about is the Unix time problem.
As some of you might have noticed, we're not addressing this problem for the first time. This is almost the same problem that we faced 20 years ago. And yeah, indeed, I'm talking about the year 2K birth. So for some of you that don't know, I'm going to quickly summarize this problem for you, as it is crucial in understanding what we're facing right now. So Y2K was also a date formatting problem, which was caused by the use of 2 digits to represent year. So as you can probably guess, the computers were not able to distinguish between the year 2000 and 1900 because they both have 00 as their year representation. This was detrimental to many services, including ATM machines that had to be forced to shut down, old cell phones which did not function correctly, or even more severely, faulty radiation monitoring software. So billions of dollars have been poured into fixing this problem, yet it resurfaced less than 20 years later. So who is to blame? In an interview with a lead engineer in Adobe about his solution to Y2K, he defended, quote, "We thought that the system would be out of date by 2020. Was he irresponsible? Well, let's go into details. There were 3 main solutions to this problem. The first is the simplest problem, is the simplest solution, use a 4-digit year format. However, this is not very straightforward, as most databases at that time had a 6-digit limit on the input. So this requires mass testing and a lot of money. So here comes the second solution, which was date repartitioning. This only uses 6-digit to represent date format, which includes 3 for the year and 3 for the ordinal date. However, there were too many legacy code that depended on the other representation, so this was merely not an option. So this leads to the most popular option, which was called date windowing. This simply uses logic to determine which event is in the 20th or 21st century. For example, if we have a law that was passed, it's probably in the 21st century, and more than 80% of companies employed this solution because of the usual limited time and money resources. So going back to the quote from the beginning, instead of finding people to blame, how do we prevent this from ever happening again?
Okay, I'm going to talk to you about a couple of solutions that can to solve this problem. So there's no one solution for this problem, because the problem has appeared for different reasons. So I'm going to focus more on the software side. So there are software problems partly because of the C standard. And its standard states that time t, which is the data type used to store Unix time, shall be an integer type. So that means it could be a 16-bit integer or a 32-bit integer, just depending on the whim of some programmer. And that's obviously bad, because as we've previously discussed, a 32-bit integer won't last past 2038. So a lot of systems are going to not function as a result. So bugs can appear in libraries which use time t. So if a library uses time t, it might mean that the library and the source code and the code using the library will have to be completely refactored, because the code using the library may actually rely on time t being a 32-bit integer. So if it's refactored, it won't be. A slightly better case is if your code just uses time t, then you just have to refactor it. But either way, a lot of work is going to have to be done.
So as for the solutions, one might argue, why not just make the integer unsigned? That would essentially double us the time, giving us giving us roughly 68 years of extra time. Basically, programs or machines that use dates before 1970 wouldn't work properly, because those dates represented as negative numbers. So this solution isn't really good. A solution that right now is pretty much working the best is pretty much transitioning to 64-bit architectures. So machines are already built this way. The whole industry is transitioning toward this higher standard. But what about machines that have 32 bits? You can't just take all of them and change the hardware. So basically, Unix and Linux are implementing 64-bit representation for time, even on machines that have 32 bits. So basically, that would pretty much solve the problem for on the next versions of Linux. The real problem right now are embedded systems. So these are systems that were never intended to be updated. So pretty much they were just built into airplanes, machines, cell phones, and really were never intended to be changed. And so a lot of these systems, because they're so small, they have 32-bit architectures, and usually are not year 2K38 safe to say. So they're a massive problem, and there isn't really an elegant solution for this. And also a massive other problem is the legacy code that uses 32-bit representation, or that was developed based on the fact that time is represented as 32 bits. All that legacy code can't really be changed or refactored, because there's code right now in the present that depends on that code.
Okay, let's just say that you've reached the 19th of January 2038 and you haven't solved the problem yet. What could go wrong? There are two ways that this overflow error can go down. The first is that the program raises an overflow exception. Some programming languages like Python check during runtime whether the signed or unsigned integer you're using exceeds a certain bound, and the program terminates immediately and you get an error message. In the year 2000, we had systems like ticket machines, cash dispensers crashing all around the world because of this exception raised. The second way is a more dangerous route. No exception is raised, and the overflow simply wraps around a modulo power of 2, and you get the incorrect date. This happens for a lot of languages like C, C++, and Java, and in C, when you add 1 to the maximum signed integer you can store, it makes the maximum negative integer. This is perhaps more dangerous than having an exception raised, because it is not immediately obvious that this error has occurred. You probably only get an inkling that something has gone wrong way down the programming pipeline, and by then it might not be obvious that your miscalculation or incorrect decision making was caused by this overflow error. Indeed, in the year 2000, a similar problem occurred in a more local area in Sheffield, where incorrect risk assessments were done for 154 pregnant women, and 2 abortions were carried out as a direct result of a white hoop Y2K bug causing miscalculations of mother's age, which predicted that they would get a baby with Down syndrome. As you can see, overflow errors can have significant impacts on a global and personal scale. If we keep having to address these overflow issues through direct legislature, task forces, and direct hardware replacements, it begs the question, could there be an ideological standard that we abide by to prevent these future occurrences of overflow errors?
So a good starting point of looking for these ideological standards is from the Code of Conduct. Nowadays we have various Code of Conducts in different computing societies, restricting professionals' actions, standardizing development process. So how are these Code of Conducts doing? Unfortunately, when we look for the BCS Code of Conduct, we can't find some relevant content. BCS Code of Conduct includes some very general guidances and don't have specific requirements, especially about quality of codes. We definitely think this is something that the BCS Code of Conduct could improve. Although it is important for Code of Conducts to be general, it is also important for them to be specific enough to address certain problems, such as the quality of codes. And when we go to the ACM Code of Ethics, we're glad to see that it has some specific requirements about the quality of codes. It states that the professionals have to recognize the potential negative impacts, and they have to be responsible for the code they write. They also need to evaluate the potential risks of their software system. This is very relevant to the year 2038 problem. If developers have carefully evaluated the potential consequences of using 32-bit data type, we could have prevented this problem. Similarly, in IEEE Computer Society Code of Conduct, it also stressed the importance of the quality of code. With these Code of Conducts, if professionals would have followed them, we expect fewer such problems would appear in the future. However, there's a real problem we would like to ask. Do these Code of Conducts actually apply to year 2038 problem? With ACM Code of Ethics or IEEE Computer Society Code of Ethics, are we indeed safe now? The first problem is, of course, that we can't expect everyone to follow these Code of Conducts. But more importantly, the real issue is that when we take a look at these Code of Ethics, they're really about software development in businesses. They emphasize employers, employees, users, clients, etc. But these Unix and Unix-like operating systems are open source or semi-open source projects. More importantly, they were just some research or personal projects. So, can we have some universal Code of Conduct for all open source projects? Our answer is definitely no, because that does not make sense. We as students, for example, probably produce lots of bad code because we're still learning. We might decide to make them open source on GitHub. Is that unethical? No, because we don't expect thousands of people using our products. Our codes are just for the sake of learning and researching. This is similar for the development of Unix and Unix-like operating systems. Bell Lab didn't expect billions of people use Unix-like operating systems. Linus didn't expect billions of people using Linux. It doesn't make sense to have specific requirements for all open source projects. But there is indeed something we can do, is that we can have Code of Conducts in important open source projects. Linux, for example, have a well-established Code of Conduct nowadays. The open source community has been working hard on improving the quality of codes, and we hope this effort will continue, so we can truly prevent similar problems in the future. Thank you.